The universe keeps its secrets locked away in the echoes of ancient starlight, each photon carrying tales older than our planet itself. But what if we could decode those messages? What if the answers to time itself are hidden in the distant glow of galaxies vanishing over the cosmic horizon? Right now, telescopes and satellites are capturing light from events that happened billions of years ago, giving us snapshots of the universe's childhood. And here's what's truly astonishing. Those images aren't just relics of the past, they're keys to understanding the very laws that govern our present. From the way galaxies spin to the way black holes bend time, every clue pulls us deeper into a story that's still being written. So let's trace those clues together, back to the moments when the universe was young, and forward to the discoveries that could redefine everything we know. The cosmos isn't just history, it's a living, breathing chronicle, and we're about to turn the page. Think of the universe not as an empty void, but as a vast, breathing entity, one that began as a single, unimaginably hot and dense speck smaller than an atom. In an instant, that speck erupted, stretching space itself faster than the speed of light. That was the Big Bang, not an explosion in space, but of space, filling the newborn cosmos with energy that would eventually cool into matter, then stars, then us. We even have a snapshot of that moment, the cosmic microwave background, a faint glow of radiation that still lingers in every direction, like an afterimage from the universe's first breath. But here's where it gets even stranger. The Big Bang didn't just create everything, it left behind puzzles that still keep scientists awake at night. For instance, what triggered it? Some researchers argue that our universe might be one bubble in an infinite multiverse, constantly sprouting new cosmic beginnings. Others propose a cyclical model, where universes collapse and rebirth in an endless loop. And then there's the question of time itself. Did it even exist before the Big Bang? Or is that like asking what's north of the North Pole? What's undeniable is how this single event set in motion the laws of physics as we know them. The forces that bind atoms, the way light travels, even the eventual formation of planets, all of it traces back to those first chaotic moments. Every star, every galaxy, even the device you're watching this on, owes its existence to that epic birth. So while we may never know exactly what sparked it all, one thing's certain: understanding the Big Bang isn't just about the past, it's about decoding the blueprint of reality itself. Stretching reality far beyond human intuition, cosmic inflation was the universe's most dramatic growth spurt, an expansion so rapid it defies our everyday understanding of speed. Picture a single grain of sand suddenly swelling to the size of our entire solar system. In less than a trillionth of a second, that's the scale we're talking about. And this wasn't just a brief anomaly. Inflation solved mysteries that the Big Bang alone couldn't explain. Take the cosmos' eerie uniformity. No matter which way we point our telescopes, the distant universe looks remarkably similar in temperature and structure, as if someone stirred it thoroughly. But here's the catch. Regions now billions of light years apart were once close enough to exchange heat, like 2 cups of coffee left to reach the same temperature. Without inflation, they'd never have had time to balance out. Only a runaway expansion could have stretched space so quickly, locking in that uniformity before these regions lost contact forever. Then there are the quantum fluctuations, tiny hiccups in the fabric of reality itself. During inflation, these random subatomic twists were stretched to cosmic proportions, becoming the gravitational seeds for everything we see today. Those faint temperature variations in the cosmic microwave background, they're the imprints of those quantum ripples later amplified into galaxies and superclusters. It's almost poetic. The largest structures in existence owe their existence to the tiniest possible wobbles in spacetime. But inflation does more than explain the past, it reshapes our future. If this theory holds, our observable universe might just be one tiny bubble in a frothing multiverse where new universes sprout endlessly. That's the bold vision some physicists now entertain. And while we can't yet prove it, every new observation, like the precise patterns in that ancient microwave glow, brings us closer to confirming whether inflation truly was the universe's defining moment. The oldest photograph ever taken wasn't captured by a camera, it was imprinted on the fabric of space itself. The cosmic microwave background, or CMB, is light that's been traveling for over 13 billion years, carrying whispers from the universe's infancy. When astronomers Arno Penzias and Robert Wilson first detected this faint static in 1965, they initially thought it was interference from pigeon droppings on their antenna. What they'd actually stumbled upon was something far more profound: the cooled remains of the Big Bang's fiery birth. This ancient glow isn't just uniform background noise. With sensitive enough instruments, we can detect subtle temperature variations, fluctuations so small they're like spotting bumps on a billiard ball the size of Earth. Yet these tiny ripples are cosmic gold. They're the fingerprints of density variations in the early universe, regions where matter ever so slightly clumped together. Over eons, gravity amplified those minute differences, sculpting them into the galaxies and galaxy clusters we see today. The CMB's near-perfect uniformity poses a fascinating puzzle. How did regions billions of light-years apart reach nearly identical temperatures without ever being in contact? This cosmic smoothness became one of the strongest pieces of evidence for inflation. That brief but unimaginably rapid expansion that ironed out the universe's wrinkles in its first split second. Without inflation, the CMB's uniformity would violate the very speed limit of the universe. Nothing, not even heat, can travel faster than light, yet mysteries remain. Why is one hemisphere of the CMB slightly cooler than the other? Could this be evidence of a pre-Big Bang universe or just a statistical fluke? Each new generation of telescopes, from Cobe to Planck, has sharpened our view of this cosmic relic, peeling back layers of its story. And as we refine our measurements, we're not just looking backward, we're testing fundamental physics in ways no laboratory ever could. The CMB isn't just light, it's a time capsule, and we're only beginning to decipher its deepest secrets. Galaxies should fly apart. That's the brutal truth astronomers realized when they measured how fast stars whirl at the edges of spiral galaxies. Their outer regions rotate so fast that the visible matter alone couldn't possibly hold them together with gravity. There had to be something else, something invisible weaving an unseen scaffold throughout the cosmos. Enter dark matter, the universe's silent architect, exerting a gravitational grip without emitting a single photon of light. What makes dark matter so baffling isn't just its invisibility, it's how common it is. For every ounce of ordinary matter, planets, stars, even our bodies, there's 5 times as much dark matter permeating space. Its gravity sculpts galaxies into their shapes, binds clusters together, and even bends light from distant objects, a phenomenon called gravitational lensing. Yet despite its overwhelming presence, dark matter refuses to interact with light or ordinary matter in any way we can directly detect. It's like trying to study a ghost by watching how it pushes against a curtain. The hunt for dark matter's identity has taken scientists to some extreme places, miles underground in abandoned mines where ultra-sensitive detectors wait for a rare collision with a hypothetical dark matter particle. Others scan the skies for anomalies like gamma-ray signatures that might hint at decaying dark matter. Then there's the radical idea that dark matter could be made of ancient black holes, forged in the universe's first chaotic seconds. But after decades of searching, no theory has yet clinched the answer. What's at stake isn't just a cosmic census, it's the foundation of physics itself. If dark matter turns out to be an undiscovered particle, It could open doors to entirely new laws of nature. Or perhaps we've misunderstood gravity altogether, and the universe is forcing us to rewrite Einstein's rules. Either way, this invisible force isn't just a missing piece of the puzzle. It's a reminder of how much we still don't know about the stage on which our cosmic story unfolds. Just when scientists thought they had cosmic expansion figured out, the universe threw another curveball. In the late 1990s, two separate teams studying distant supernovae made an unsettling observation. The universe wasn't just expanding, it was speeding up. It was as if some invisible force had pressed the cosmic gas pedal, pushing galaxies apart faster and faster. That force has a name: dark energy. Here's what makes it so strange. Unlike dark matter, which pulls things together with gravity, dark energy does the opposite. It repels. Think of it like anti-gravity woven into the fabric of space itself. And its influence is staggering. Dark energy makes up roughly 68% of the universe's total energy, yet we have no idea what it actually is. The leading theory suggests it might be a property of empty space, an inherent energy that grows as the universe expands, but that raises even wilder questions. If this energy increases over time, could it eventually tear atoms apart in a catastrophic Big Rip? Some physicists speculate dark energy might not even be constant. It could fluctuate, or even change the rules of physics in distant corners of the cosmos. Others wonder if it's tied to mysterious particles or dimensions we've yet to discover. What's undeniable is that dark energy isn't just a footnote in cosmology. It's rewriting our understanding of the universe's fate. Every galaxy, every star, every speck of dust is caught in this tug of war between gravity's pull and dark energy's relentless push, a battle that will determine whether the cosmos ends in fire, ice, or something far stranger. While dark energy remains one of science's greatest enigmas, its discovery was a humbling reminder. The universe still holds cards close to its chest. And if we've learned anything, it's that the deeper we look, the more surprises await. Some of the most breathtaking spectacles in the universe aren't explosive deaths of stars, but their births. Hidden inside sprawling, ink-black clouds of molecular gas and dust, a silent battle plays out between gravity and pressure. When gravity wins, it crushes atoms so tightly that hydrogen begins fusing into helium, igniting a nuclear furnace that will shine for millions or even trillions of years. Welcome to stellar nurseries, the cosmic cradles where stars are born. Take the Orion Nebula, a glowing stellar factory just 1,500 light-years away. To the naked eye, it's a faint smudge in Orion's sword, but through a telescope, it reveals a chaotic dance of newborn stars, their fierce radiation carving cavities in the surrounding gas like cosmic blowtorches. Some of these stars are monsters dozens of times heavier than our Sun, blazing so intensely they'll burn out in just a few million years. Others are modest red dwarfs, destined to outlive every galaxy we've ever observed. What determines a star's fate? It's all about the starting conditions. Turbulence within a collapsing gas cloud fragments it into clumps, each destined to become a star. Denser clumps attract more material, growing massive and hot enough to ignite fusion rapidly. Smaller ones take longer, sipping fuel so slowly they'll glow faintly for eons. And sometimes, these nurseries don't produce solitary stars, they birth dazzling clusters, siblings bound together by gravity until galactic tides eventually pull them apart. The legacy of these nurseries goes far beyond starlight. When massive stars die, they scatter heavy elements: carbon, oxygen, iron forged in their cores across space. These elements become the raw materials for planets, oceans, and even life itself. Every atom in our bodies was once part of a star that lived and died long before Earth existed. So when we peer into a stellar nursery like Orion, we're not just witnessing creation, we're glimpsing our own cosmic ancestry, written in the glow of newborn suns. A star's life might seem eternal on human timescales, but like all things, it has an expiration date. For billions of years, stars like our Sun burn steadily, balancing gravity's inward crush with the outward pressure of nuclear fusion, a cosmic tug-of-war that defines the main sequence phase. But when the hydrogen in their cores finally dwindles, the delicate equilibrium shatters, and the star's fate hinges on a single factor: its mass. Take a star like our Sun. Once its core hydrogen is exhausted, it swells into a red giant, its outer layers puffing out far enough to engulf Mercury and Venus. For a brief, fiery moment, it even fuses helium into carbon and oxygen. But without the mass to go further, it eventually sheds its outer layers in a shimmering planetary nebula, leaving behind a dense, Earth-sized ember, a white dwarf. This stellar corpse will cool over trillions of years, fading into darkness like a forgotten campfire. Now, imagine a star many times more massive. Its demise is far more violent. After burning through heavier elements, helium, carbon, even iron, its core collapses in seconds, triggering a cataclysmic supernova. The explosion unleashes more energy than the star emitted in its entire lifetime, briefly outshining entire galaxies. In that maelstrom, atoms are forged into gold, uranium, and other heavy elements before being hurled into space. This stellar alchemy is why we find traces of ancient supernova in everything from meteorites to our own bones. Yet the drama doesn't end there. What remains of the core depends on its weight. If it's between 1.4 and 3 solar masses, it crushes into a neutron star, a city-sized object so dense that a teaspoon of its material would weigh 1 billion tons. More massive still, the collapse continues, warping spacetime itself into a black hole. These extreme remnants aren't just cosmic curiosities, they're the engines powering some of the universe's most energetic phenomena. From the ashes of dead stars rise the building blocks of new worlds and life itself. Every element heavier than iron, every speck of oxygen in our lungs, every piece of jewelry we wear was forged in these final, furious moments. Stars may die, but in their deaths they gift the cosmos with the ingredients for rebirth. The cosmic aftermath of a supernova doesn't always end with silence. Sometimes it leaves behind a spinning, hyper-dense remnant so extreme it defies common sense, a neutron star. Picture taking all the mass of our Sun and cramming it into a ball no wider than Manhattan. The result, an object with gravity so intense it warps the very fabric of space around it. At the heart of a neutron star, atoms don't just get squeezed, they're obliterated. Electrons and protons merge into neutrons under pressures so unfathomable that a single sugar cube-sized chunk would outweigh Mount Everest. That leftover core spins furiously, often hundreds of times per second, emitting beams of radiation like a cosmic lighthouse. When those beams sweep across Earth, we detect them as pulsars, some of the most precise natural clocks in the universe, ticking with near-perfect regularity. But the strangeness doesn't stop there. When two neutron stars spiral toward each other, their collision unleashes more than just a flash of light. It shakes spacetime itself, sending ripples through the cosmos as gravitational waves. These cataclysmic mergers forge heavy elements like gold and platinum, scattering them into space to later become part of planets and even the rings on our fingers. The interior of a neutron star remains one of physics' greatest mysteries. Some theories suggest that under such crushing pressure, neutrons break apart into a soup of quarks, a state of matter that doesn't exist anywhere else in nature. Others speculate about bizarre hybrids of superconducting fluids and crystalline crusts. Every pulsar's flicker, every gravitational wave detection, brings us closer to understanding what truly happens inside these cosmic pressure cookers. Neutron stars are more than just stellar corpses. They're cosmic alchemists, timekeepers, and laboratories for the most extreme physics imaginable. And as we'll soon see, their existence is just the prelude to something even more mind-bending: the enigma of black holes, where gravity wins the ultimate battle against reality itself. At the edge of our cosmic understanding lies a phenomenon so extreme that it twists the laws of physics into knots: the black hole. Born from the death throes of massive stars or lurking in the hearts of galaxies, these gravitational monsters don't just bend space-time, they shred it. When a collapsing star's core outweighs 3 suns, no force in nature can stop its implosion. The result, a point of infinite density, a singularity where gravity becomes so overwhelming that it carves a bottomless pit in the fabric of reality. For decades, black holes were purely theoretical. Einstein's equations hinted at their existence, but even he doubted nature would permit something so bizarre. Then came the proof: Cygnus X1, a cosmic beacon emitting X-rays as it siphoned gas from a companion star. That was just the beginning. In 2019, the Event Horizon Telescope unveiled the unthinkable: a glowing ring of light encircling the shadow of supermassive black hole M87, a portrait of gravity's triumph over light itself. Yet the more we uncover, the stranger black holes become. Cross the event horizon, and the universe as we know it unravels. Time stretches to a standstill for outside observers, while anyone falling in would be shredded by tidal forces, or maybe not. Some theories suggest quantum effects could turn the horizon into a fiery wall of energy. Others propose that singularities might birth wormholes, tunnels to distant regions, or even other universes. Could black holes be cosmic recycling centers, crunching matter down only to spit it out elsewhere? The collisions of black holes add another layer of wonder. When 2 of these invisible giants spiral into each other, they churn space-time itself, sending out gravitational waves, ripples we've now detected with instruments like LIGO. Each merger is a violent tango that briefly outshines all the stars in the observable universe combined. What lies at the heart of a black hole remains the ultimate enigma. String theory suggests a fuzzy fuzzball of tangled strings instead of a singularity. Holographic principal arguments claim all the information swallowed might be encoded on the event horizon surface. One thing's certain: black holes aren't just cosmic oddities, they're relentless experiments, testing the limits of relativity, quantum mechanics, and our very notion of reality. And with every discovery, they force us to rewrite the rules. Crossing the event horizon isn't like stepping over a line. It's more like sailing toward a waterfall in total darkness, unaware of the point where the current becomes inescapable. This invisible boundary around a black hole marks the ultimate point of no return. Once matter, light, or even time itself passes through, there's no coming back. The laws of physics as we know them seem to unravel here, creating paradoxes that challenge our deepest understandings of reality. From an outside observer's perspective, something even stranger happens. As an object approaches the event horizon, time stretches to a near standstill. A clock falling into a black hole would appear to tick slower and slower, frozen at the threshold from our point of view. Yet for the doomed traveler, time marches on relentlessly toward the singularity. This eerie effect isn't science fiction. It's a direct consequence of Einstein's general relativity, where gravity warps the very fabric of time. But black holes aren't the perfect traps they seem. In the 1970s, Stephen Hawking revealed that they slowly leak energy through quantum fluctuations near the horizon. These ripples, now called Hawking radiation, mean black holes aren't eternal. They evaporate over incomprehensible timescales, leaving behind only whispers of their existence. Yet this revelation came with a haunting question. What happens to the information swallowed by the black hole? Quantum physics insists that information can't vanish, but general relativity suggests it's lost forever in the singularity. This clash between two foundational theories, the infamous information paradox, remains one of the most heated debates in physics. Some theorists argue the answer lies on the event horizon itself, where quantum entanglement might encode swallowed data like a scrambled hologram. Others propose that black holes tunnel into baby universes, carrying information into entirely separate realities. Whatever the truth, the event horizon isn't just a cosmic dead end. It's a laboratory for testing the boundaries of physics, forcing us to rethink the nature of space, time, and information itself. And while black holes may seem like distant oddities, their influence stretches far beyond their own dark hearts. They shape the galaxies they inhabit in ways we're only beginning to grasp. Deep in the heart of the Milky Way, hidden behind thick veils of dust and stars, lies a sleeping giant, Sagittarius A. With a mass 4 million times that of our Sun, this supermassive black hole dominates our galactic center. But despite its staggering size, it's remarkably quiet, only occasionally flaring as it swallows stray gas or unfortunate stars. Not all galactic cores are so calm. Some supermassive black holes are cosmic powerhouses, launching jets of energy so intense they can outshine their entire host galaxies. How did these gravitational titans get so enormous? One theory points to the early universe, where massive clouds of gas may have collapsed directly into black holes without forming stars first, a kind of cosmic shortcut. Others grew over billions of years, gorging on gas and merging with smaller black holes like celestial snowballs. Some may even have been seeded by ancient, supermassive stars unlike anything we see today. Whatever their origins, their influence is undeniable. When supermassive black holes feed, they don't just consume, they reshape their surroundings. Their gravity can fling stars into chaotic orbits, while the energy from their accretion disks flood space with radiation. In some galaxies, powerful jets erupt from the poles at nearly light speed, carving bubbles in intergalactic gas millions of light years wide. These outbursts can either trigger furious bursts of star formation or snuff it out entirely, leaving galaxies sterile and silent. The Milky Way's own supermassive black hole may seem dormant now, but it hasn't always been so well behaved. Evidence suggests it flared violently in the past, with echoes of its outbursts still visible in the radiation-scarred gas clouds around it. And one day, when the Andromeda Galaxy collides with ours in about 4 billion years, Sagittarius A could wake from its slumber, merging with Andromeda's black hole in a cataclysm that will reshape our galactic home. Studying these giants isn't just about understanding black holes, it's about piecing together the life story of galaxies themselves. Every flicker, every jet, every ripple in spacetime they create is a clue to how the universe builds and sometimes destroys the grand structures we see today. At the edge of observable space, where light takes billions of years to reach us, cosmic beacons blaze with the brilliance of 1 trillion suns. These are quasars, nature's ultimate powerhouses, fueled by supermassive black holes in their most voracious phase. Imagine a single object so luminous it drowns out the combined light of every star in its host galaxy. That's the staggering reality of these ancient monsters, whose light has traveled across eons to reach our telescopes. What makes quasars truly extraordinary isn't just their brightness, it's the physics behind their fury. As gas, dust, and even whole stars spiral toward the black hole's event horizon, friction heats the infalling material to millions of degrees, creating a swirling disk of plasma that glows brighter than anything else in the cosmos. Some quasars eject twin jets of charged particles at nearly light speed, stretching hundreds of thousands of light years into intergalactic space. These jets act like interstellar blowtorches, carving through galaxies and sculpting the universe's large-scale structure. Yet quasars weren't always this rare. In the universe's youth, they were far more abundant, their golden age peaking just a few billion years after the Big Bang. Back then, galaxies were gas-rich, providing endless fuel for their ravenous black holes. But as the cosmos aged, star formation consumed much of this raw material, and mergers became less frequent, leaving many supermassive black holes to starve in near darkness. Today, spotting a quasar feels like catching the final embers of a cosmic wildfire that once blazed across the early universe. Their fading brilliance holds vital clues. By studying quasars, astronomers can trace how galaxies and their central black holes evolved together, a dance of destruction and creation that shaped everything we see. The light from these distant beacons carries fingerprints of the gas clouds it passed through, allowing us to map the universe's hidden scaffolding. As we peel back the layers of these radiant enigmas, one truth becomes clear: quasars are more than just relics of a violent past. They're the key to understanding how the universe transformed from a sea of primordial gas into the intricate web of galaxies we see today. And with every new discovery, they remind us that even the brightest lights in the cosmos are fleeting, leaving behind echoes of their glory in the darkness. In the beginning, galaxies weren't grand spirals or blazing ellipticals. They were merely faint ripples in the darkness. Picture the early universe as a vast, nearly uniform sea of hydrogen and helium, dotted with tiny pockets where matter clustered ever so slightly. Those slight overdensities were the seeds of everything we see today. Over billions of years, gravity amplified them, pulling in gas and dark matter until swirling disks and glowing spheres emerged, each one a galaxy in the making. Take our Milky Way. Its elegant spiral arms didn't appear overnight. They grew from a delicate dance between rotation and gravity, gas flattening into a disk as it circled the galactic center, while dark matter formed an invisible halo, anchoring everything together like cosmic scaffolding. But not all galaxies follow this script. Some, like giant ellipticals, are chaotic balls of ancient stars, their random orbits hinting at violent past. The difference: collisions. When two spirals collide, their gas clouds slam together, igniting bursts of new stars while gravity scrambles their orderly orbits into a frenzied swarm. Yet mergers don't always spark creation. Sometimes they snuff it out. If a galaxy runs out of cool gas, star formation grinds to a halt, leaving it full of aging red stars but no new ones. This might explain why some ellipticals are cosmic graveyards, their stellar nurseries long exhausted. Others, like the Milky Way, keep a steady supply of gas, allowing them to birth stars for billions of years. Our own galaxy's history is written in the motions of its stars. Some move in neat, circular orbits, while others dart wildly, remnants of past mergers. And the story isn't over. In 4 billion years, the Milky Way will collide with Andromeda, their gravitational tango likely birthing a massive elliptical galaxy. But why do some mergers make spirals while others destroy them? The answer lies in a mix of dark matter's grip, the luck of gas supply, and the precise angle of collision. Galaxies aren't just collections of stars, they're living records of the universe's history, each one shaped by the forces of gravity, chance, and time. And as we unravel their stories, we learn not just how they formed, but how we came to be here, watching them from a tiny spiral arm in the cosmic tapestry. From our vantage point on Earth, the Milky Way often appears as a pale, shimmering band across the night sky, but zoom out, and the true grandeur of our galactic home comes into focus. Picture an immense barred spiral, stretching 100,000 light-years from end to end, with 4 sweeping arms curving outward from a bright central bar. Our solar system sits tucked away in the Orion Arm, a quiet suburban neighborhood of the galaxy, far removed from the chaotic energy of the crowded core. What's truly astonishing is the sheer scale of the Milky Way's population. an estimated 100 billion stars, each with its own potential worlds. Yet even that staggering number pales in comparison to the unseen mass lurking in the galactic halo, dark matter, an invisible scaffold that holds everything together. Orbiting this halo are ancient relics, globular clusters, dense balls of stars dating back nearly as far as the universe itself. These clusters are like cosmic time capsules, preserving the conditions of the galaxy's earliest days. Mapping the Milky Way presents a unique challenge because we're trapped inside it, like trying to draw the blueprint of a house while standing in one room. That's where missions like Gaia come in. This space observatory has precisely measured the positions and movements of over 1 billion stars, allowing astronomers to reconstruct our galaxy's past and trace its formation. We now know the Milky Way didn't spring into existence fully formed. It grew by consuming smaller galaxies, their remnants still visible in the stellar streams winding through the halo. At the galaxy's heart lies the ultimate Enigma, Sagittarius A, the supermassive black hole anchoring everything together. While relatively quiet now, its gravitational pull shapes the orbits of millions of stars, and its flares of activity hint at a more turbulent past. The closer we look, the clearer it becomes. Our galaxy is a living, evolving entity shaped by collisions, star births, and the unseen hand of dark matter. Understanding the Milky Way isn't just about astronomy. It's about knowing our place in the universe. Every atom in our bodies, every element that makes up our planet, was forged in the hearts of stars that lived and died long before Earth existed. We are quite literally the galaxy's way of understanding itself. Something beyond the edge of our universe is tugging at entire clusters of galaxies, pulling them in a direction that defies all expectations. This eerie motion, known as dark flow, was first detected in 2008, when astronomers noticed hundreds of massive galaxy clusters drifting at astonishing speeds toward the same patch of sky. Not just a gentle drift, either some were moving over 2 million miles per hour. The unsettling part, there's nothing visible in that direction with enough gravity to explain it. This isn't how the universe is supposed to behave. According to the standard model of cosmology, the expansion of space should distribute galaxies evenly in all directions, like raisins in rising bread dough. Yet dark flow suggests something massive, something unseen, is exerting a gravitational pull from beyond our cosmic horizon. One radical possibility. That we're feeling the tug of another universe, one of countless bubbles in a vast multiverse. If true, that would mean our cosmos isn't an isolated island. It's just one piece of a far grander structure. Skeptics argue it could be a statistical anomaly or a flaw in how we measure cosmic velocities. But the data keeps mounting. Subsequent studies have confirmed peculiar motions in galaxy clusters, with some even suggesting the flow extends farther than we once thought, billions of light years beyond where our telescopes can peer. That's the haunting beauty of dark flow. It forces us to confront the limits of our knowledge. If the effect is real, it implies there are entire regions of space-time, perhaps even other universes, whose gravity leaks into ours like whispers through a wall. What lies in that mysterious direction? A supercluster of unimaginable scale, a cosmic defect left over from the Big Bang, or evidence that our universe is just one thread in an infinite tapestry? Until we have answers, dark flow remains one of cosmology's most tantalizing riddles, a reminder that the universe still holds cards we haven't even glimpsed yet. And if this motion really is a fingerprint of the multiverse, it could mean the biggest revolution in physics since relativity. Now, let's push further into the unknown, because if dark flow hints at parallel universes, the multiverse theory might just be the key to unlocking them. The idea of a single, solitary universe feels almost quaint when you consider the radical alternative. What if ours is just one page in an infinite cosmic library? This is the multiverse theory, a concept that stretches from the edges of philosophy to the frontiers of theoretical physics. It suggests that beyond our observable universe, there may be countless others, each with its own unique laws, constants, and even dimensions. Some might be barren voids, devoid of stars or structure. Others could harbor forms of life we can't begin to imagine. And in a few, the conditions might be so bizarre that time flows backward or gravity pushes instead of pulls. The roots of this idea aren't pulled from science fiction, they're grounded in real physics. Cosmic inflation, the same process that smoothed our early universe, could have spawned countless bubble universes, each inflating independently like froth in an ocean. String theory takes it further, proposing a multiverse where every possible variation of physical laws exists across higher dimensions. Even quantum mechanics hints at parallel realities every time a particle makes a random choice. Some interpretations suggest the universe splits, creating alternate timelines. But here's the most haunting implication. If the multiverse is real, it could explain why our universe seems improbably fine-tuned for life. The strength of gravity, the mass of an electron, even the amount of dark energy tweak any of these by a fraction, and stars, planets, and life itself might never exist. In a multiverse, there's no mystery. We simply live in one of the rare universes where the numbers lined up perfectly. The rest, they might be cosmic dead ends, silent and empty. The real challenge is proof. How do we detect something fundamentally beyond our cosmic horizon? Some scientists scan the cosmic microwave background for bruises, anomalies that could mark collisions with other bubble universes. Others listen for subtle patterns in gravitational waves, echoes of unseen dimensions, and a few propose that dark flow, the mysterious drift of galaxy clusters, might be the gravitational tug of a neighboring universe. Whether the multiverse is a profound truth or a beautiful speculation, it forces us to confront the deepest question of all. Are we the lone experiment in existence, or just one thread in an unimaginably vast tapestry? The answer, if we ever find it, could redefine not just science but our place in reality itself. The universe hums with hidden music, not from stars or galaxies, but from strands of energy trillions of times smaller than an atom. This is the bold vision of string theory, a radical idea that rewrites the building blocks of reality. Forget tiny dots like electrons or quarks, picture every particle as a microscopic, vibrating string. The pitch of these vibrations isn't just artistic flair. It determines whether a string plays the note of an electron, a photon, or even the elusive graviton, the hypothetical carrier of gravity. In this symphony of the smallest scales, the universe's deepest laws could emerge from nothing more than harmonies in the fabric of space-time. But there's a catch: string theory doesn't work in the familiar 3 dimensions of space and 1 of time. To make the math sing, physicists had to introduce 6 extra dimensions, curled up so tiny they'd be invisible even to the most powerful particle colliders. Imagine an ant crawling along a telephone wire. From far away, the wire seems one-dimensional, but up close, the ant senses the wire's full cylindrical shape. Our universe might hide similar unseen folds, wrapped into intricate shapes called Calabi-Yau manifolds. Some variations of the theory propose even wilder possibilities. What if these extra dimensions aren't small at all, but vast, with our entire universe just a 3-dimensional brain, floating like a sheet of paper in a higher dimensional space? Collisions between brains could have sparked events like the Big Bang, and gravity might leak between them, explaining why it's so weak compared to other forces. Yet for all its elegance, string theory has a thorny problem: proof. The energy scales needed to detect strings are far beyond our current technology, leaving the theory in a frustrating limbo between beauty and testability. That hasn't stopped physicists from exploring its staggering implications. The theory's landscape of possible solutions, perhaps 10 to the 500th power variations, suggests a multiverse where every conceivable set of physical laws exists somewhere. Whether string theory is the ultimate framework of reality or a mathematical mirage, it's already reshaped how we think about space, time, and the very nature of existence. And as we'll soon discover, time itself might hold dimensions we've yet to imagine. Time slips through our fingers differently depending on where or how fast we're moving. Imagine two identical clocks, one placed on Earth's surface, the other launched into orbit aboard a GPS satellite. After just one day, the orbiting clock ticks ever so slightly faster by about 45 microseconds simply because it's farther from Earth's gravity and moving at nearly 4 kilometers per second. Without correcting for this effect, your phone's navigation would drift off course by roughly 10 kilometers per day. This isn't a glitch, it's Einstein's theory of relativity in action, proving time isn't a rigid backdrop but a fluid, malleable dimension shaped by speed and gravity. The closer you get to a black hole's event horizon, the more extreme time distortion becomes. An astronaut hovering near the edge might experience just 1 hour passing, while centuries unfold for observers back on Earth. This isn't theoretical. Scientists have observed time dilation in action, like when fast-moving cosmic particles called muons survive longer than they should because their high speeds stretch time from our perspective. But what if we could harness this phenomenon? For interstellar travel, near light-speed journeys could let astronauts reach distant stars in what feels like years, while millennia pass on Earth. The catch: energy requirements are unfathomable, and returning would mean finding a world you no longer recognize. Some physicists speculate about using intense gravitational fields as natural time machines, though the forces involved would tear any known material apart. Beyond the equations, time dilation forces us to confront the nature of reality itself. If time can stretch and compress, is the present truly universal or just a local illusion? The answers might lie not just in physics labs but in the depths of black holes where the fabric of time itself frays at the edges. The fabric of space-time isn't just a static stage, it bends, warps, and might even fold. Picture a sheet of paper with two dots drawn on opposite ends. Normally, traveling between them would mean following the full length of the page. But what if you could pinch the paper, bringing those dots together and punching a hole straight through? That's the essence of a wormhole, a cosmic shortcut linking distant points in the universe, or even different moments in time. Einstein's equations of general relativity don't rule out these tunnels. In fact, the math suggests they could exist as bridges between black holes, known as Einstein-Rosen bridges. But there's a catch. Keeping a wormhole stable requires something called exotic matter, a material with negative energy that defies gravity's pull. Think of it like an anti-collapse mechanism, propping open the throat of the tunnel against the crushing weight of space-time itself. The problem? Exotic matter isn't just rare, we're not even sure it exists outside of quantum experiments where particles briefly flash into and out of reality. Even if wormholes could form, they'd come with risks. Pass through one, and you might face deadly tidal forces or sudden collapse, trapping you in an inescapable void. And then there's the ultimate headache: time paradoxes. If a wormhole connects not just space but different times, could you alter the past in ways that erase your own future? The equations don't forbid it, but the consequences would rewrite causality itself. Yet the allure of wormholes persists. Science fiction thrives on them, from Interstellar's Gargantua to Stargate's interstellar portals. But could they ever be more than plot devices? Some physicists speculate that advanced civilizations might stabilize wormholes using techniques we can't yet fathom, weaving them into a galactic transit network. Others argue they're purely mathematical quirks, vanishing under the scrutiny of quantum mechanics. For now, wormholes remain tantalizing mysteries, bridges between the possible and the fantastical. Whether they're cosmic dead ends or the future of interstellar travel, they force us to confront a profound truth. The universe is far stranger than we've dared to dream. The cosmos should be teeming with life, with hundreds of billions of galaxies, each hosting billions of stars, many circled by Earth like worlds. The numbers alone suggest we shouldn't be alone. And yet, when we scan the skies for signals, eavesdrop on radio waves, or peer through telescopes, we're met with silence. This unsettling contradiction is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One possibility is chilling advanced civilizations might not survive long enough to make contact. Technological progress could come with self-destructive risks, from nuclear war to runaway artificial intelligence. If most civilizations hit a great filter, a catastrophic barrier preventing their long-term survival, that could explain the eerie quiet. Humanity itself may be approaching such a threshold, making this more than just an academic puzzle. Then there's the zoo hypothesis, the idea that extraterrestrial societies know we're here but deliberately avoid contact, treating Earth like a protected wildlife reserve. Perhaps they're waiting for us to reach a certain level of maturity, or avoiding interference to let us evolve naturally. Alternatively, spacefaring civilizations could be so advanced that their technology is unrecognizable to us. Instead of radio signals, they might communicate through entangled particles or manipulate dark matter in ways we can't yet detect. Distance itself could be the ultimate obstacle. Even if civilizations thrive, the gulfs between stars are so vast that two species might rise and fall before a single signal crosses the void. Imagine two fireflies blinking in the night, separated by an ocean, each unaware of the other's existence. But the most humbling answer might be the simplest. Life, especially intelligent life, could be rarer than we think. The universe might be filled with microbial organisms, with complex intelligence emerging only under miraculous conditions. Or perhaps Earth is among the first, a cosmic early bloomer in a universe still waking up to its potential. Whatever the truth, the Fermi paradox forces us to confront our place in the cosmos. Are we destined to be alone, or merely waiting for the universe to answer? As we search for clues, the silence itself speaks volumes, not just about the stars, but about our own future among them. Now, let's shift our gaze from the mysteries of alien life to an even grander question. What ultimate fate awaits the universe itself, far in the future, so distant it makes the age of dinosaurs seem like yesterday? The universe will exhale its final breath. Stars, those brilliant beacons that have illuminated the cosmos for billions of years, will flicker out one by one. Galaxies, now ablaze with light, will fade into darkness like dying embers. Even the mightiest black holes, having feasted on matter for eons, will eventually evaporate into faint whispers of radiation. This isn't a dramatic explosion or a fiery collapse. It's the slow, inevitable surrender to entropy, a state scientists call heat death. At its core, heat death is a story of energy's relentless spread. Every star that burns, every galaxy that spins, every life form that thrives, all of it relies on energy moving from concentrated sources into diffuse waste heat. Eventually, there will be no more gradients left to exploit, no usable energy to harness. The universe will reach thermodynamic equilibrium, a lukewarm, featureless sea where nothing changes, nothing moves. Space itself will stretch so thin that even the distance between particles becomes insurmountable, locking the cosmos in a perpetual freeze. But what about life? Could intelligence survive in such a frozen wasteland? Some theorists have proposed audacious workarounds, like tapping into the Hawking radiation of evaporating black holes as a last-ditch power source. Others speculate about civilizations so advanced they could manipulate entropy itself, creating pockets of order in an otherwise lifeless void. Yet even these Hail Mary solutions have limits. Without usable energy, computation, and by extension, thought must eventually cease. Time, deprived of meaningful change, might become an abstract concept, like trying to measure the length of an endless, featureless plane. The unsettling beauty of this scenario isn't just its inevitability, but what it reveals about the universe's nature. Everything builds, evolves, and thrives on borrowed time, a temporary rebellion against the cosmic tide of disorder. Heat death is the ultimate reminder that all things, even the universe itself, are fleeting. And yet, in the face of such vast stillness, the fact that we exist now, to marvel at starlight, to chase understanding, to wonder what comes next, feels nothing short of miraculous. So while the universe's final chapter may be written in cold silence, the story we're part of today is anything but. And that right here, right now, is where the real magic lies. The universe's fate might not be written in ice after all. While heat death is the leading forecast, some cosmologists argue the cosmos could meet a far more violent end, one where gravity turns traitor and pulls everything back into oblivion. Known as the Big Crunch, this scenario flips the script entirely. Instead of fading into darkness, the universe would reverse its expansion, collapsing in on itself like a deflating balloon. Galaxies would rush toward each other, merging in a firestorm of collisions. Temperatures would soar until atoms themselves unravel, condensing all matter back into a single, searing point, a cosmic reset button that might even trigger another Big Bang. Yet there's another, even more brutal possibility. What if dark energy, the mysterious force accelerating the universe's expansion, doesn't just persist but grows stronger over time? In this nightmare scenario, dubbed the Big Rip, the repulsive force of dark energy would eventually overwhelm everything. First, galaxy clusters would be ripped apart, then individual galaxies. Stars would be shredded from their solar systems, planets torn from their orbits. In the final moments, even atoms and subatomic particles would be stretched to breaking point, space-time itself fractured beyond repair. The universe wouldn't just fade, it would explode from the inside out. So which of these apocalyptic endings holds more weight? The answer hinges on dark energy's true nature, a puzzle that remains unsolved. Is it a constant force, as Einstein once proposed, or something dynamic that fluctuates over time? Current observations slightly favor a gradual heat death, but the margin of error leaves room for surprises. The fact that we're even debating these extremes underscores how little we truly grasp about the forces shaping cosmic destiny. These aren't just abstract thought experiments. The stakes couldn't be higher. The fate of everything hinges on the subtle tug of war between dark energy's push and gravity's pull. And with each new telescope, each deeper probe into the cosmos, we gather more clues to this grandest of mysteries. One day, we might finally know whether the universe ends with a whisper, a crunch, or a rip. Until then, the uncertainty itself is a thrilling reminder. The story of the cosmos is still being written. The universe has ended before, not once but countless times. That's the breathtaking claim of cyclic cosmology, a radical reimagining of cosmic history where the Big Bang isn't the beginning, but merely the latest resurgence in an endless loop of destruction and rebirth. Picture a cosmic phoenix perpetually collapsing into a fiery singularity only to explode outward again, each cycle rewriting the laws of physics in subtle new ways. It's an idea as old as Hindu cosmology's days and nights of Brahma, yet modern physics has given it startling new credibility. At the heart of this theory lies a dance between dark energy and gravity. In one version, proposed by physicists Paul Steinhardt and Neil Turok, each cycle begins when the universe's expansion slows just enough for dark energy to decay, allowing gravity to pull everything back into a big crunch. But instead of vanishing into oblivion, the universe rebounds in a new Big Bang, not from a singularity, but from a collision between our three-dimensional universe and a hidden parallel dimension in a higher dimensional space. The result, a fresh cosmos inheriting faint echoes of its predecessor's structure, but with tweaked constants and reshuffled particles. The most tantalizing clue might be hiding in gravitational waves. If ripples from a previous cycle survived the last Big Bang, they could imprint faint, circular patterns in the cosmic microwave background, ghostly fingerprints of a universe that came before ours. Some researchers even speculate these waves could carry encoded data about earlier iterations, like cosmic hieroglyphs waiting to be deciphered. Yet cyclic models face fierce skepticism. For one, entropy, the universe's tendency toward disorder, presents a glaring problem. If each cycle increases chaos, shouldn't the universe eventually fizzle out? Proponents counter that black holes might reset entropy by swallowing it whole, or that the crunch itself could erase the slate clean. Others argue that without observable proof, the theory remains more poetry than physics. Whether cyclic cosmology holds up or not, it challenges our deepest assumptions. If time isn't linear but circular, does the beginning even mean anything? And if the laws of physics are mutable, could our universe be just one variation in an infinite series of experiments? The answers might rewrite not just cosmology, but the very nature of existence itself. Picture this: you wake up one morning and the world around you feels off. Maybe gravity stutters for a fraction of a second, or you catch a fleeting glimpse of pixels in the corner of your eye. These could be nothing, or they might be telltale signs that reality isn't what it seems. Welcome to simulation theory, the mind-bending idea that our entire universe, every galaxy, every atom, even your thoughts, could be nothing more than lines of code in an unfathomably advanced computer program. It's not just science fiction. Prominent figures like Elon Musk and philosopher Nick Bostrom have seriously entertained the idea. Their reasoning: if civilizations inevitably develop the power to create hyper-realistic simulations of their ancestors, and they run countless iterations of them, the odds are overwhelming that we're in one of those simulations rather than the original reality. Think of it like video games. In the 1970s, Pong's 2 paddles and a dot were cutting edge. Today, we have photorealistic worlds with AI-driven characters. Extrapolate that progress over thousands or millions of years. Couldn't a future civilization simulate an entire universe? Skeptics point out the glaring hole in this argument. There's no way to definitively test it. But intriguingly, some physicists speculate that tiny anomalies in quantum mechanics, like the way particles behave differently when observed, might hint at underlying computational rules. Even cosmic rays, those high-energy particles from deep space, could theoretically carry evidence if they behave in ways that resemble error correction protocols in a vast simulation. The implications are staggering. If we're living in a simulation, who's running it? Are we someone's ancestor simulation, an alien school project, or an AI's attempt to understand its own origins? And more unsettling, could the simulation ever be shut down? Whether you find the idea thrilling or unsettling, simulation theory forces us to confront the deepest question of all: what is reality? Until we uncover proof one way or another, the universe remains the ultimate mystery, programmed or not. Now, let's take a step further, because if reality is a construct, the nature of consciousness itself might be the next puzzle to unravel. At the smallest scales of the universe, reality doesn't behave the way we expect. It flickers. Electrons, photons, and other quantum particles don't exist as neat, solid objects with defined positions. Instead, they linger in a ghostly haze of possibilities, spread out like ripples in a pond until the moment we measure them. Only then does this probability wave collapse into a single, concrete outcome. It's as if the universe hesitates until someone or something pays attention. Physicists call this the observer effect, and its implications are anything but small. This phenomenon isn't just a quirk of math, it's been tested repeatedly with experiments like the famous double slit, where particles behave as waves until observed, then abruptly choose a path. But here's where things get really strange. The observer doesn't have to be human. A detector, a camera, even another particle can trigger the collapse. So what is observation, really? Some interpretations, like the Copenhagen view, argue reality remains undefined until measurement forces it into existence. Others, like the many worlds theory, propose that every possible outcome does happen just in branching parallel realities where each version plays out. Then there's the radical idea that consciousness itself might be the key. Could the universe fundamentally require observers to give it shape? This isn't mysticism, it's a genuine debate in physics, where the boundary between measurement and meaning starts to blur. Yet skeptics push back. Maybe the observer effect is just a consequence of how quantum systems interact, nothing more. Quantum mechanics forces us to confront a humbling truth. The deeper we probe, the less certain reality becomes. Particles pop in and out of existence. Entangled photons influence each other instantly across vast distances, defying classical notions of space and time. Even the vacuum of space isn't empty, it crackles with temporary particles borrowing energy from the future. What does it all mean? Maybe the universe isn't a fixed stage but a dynamic, participatory dance. One where the act of observation isn't just passive witnessing, but an integral part of the performance. Whether that hints at deeper layers of existence or simply reflects the limits of our current understanding, one thing's clear: the quantum world refuses to play by our everyday rules. And in that refusal, it opens doors to possibilities we're only beginning to imagine. Here's the next section of your script, crafted to flow seamlessly from the previous segments while diving into the fascinating concept of the anthropic principle. Out of all possible universes, why does ours seem tailor-made for life? Tweak the strength of gravity by even 1%, and stars might never form. Adjust the cosmological constant by a hair, and galaxies wouldn't coalesce. This eerie precision isn't coincidence, it's the anthropic principle in action. The idea that the universe's constants appear fine-tuned because we're here to notice them. In a cosmos where the slightest deviation would render life impossible, our very existence becomes a clue to the deepest workings of reality. But is this explanation satisfying or a cosmic shrug? Some scientists argue it's circular reasoning. We exist because the universe permits life, and the universe permits life because we exist. Others see it as a gateway to something grander. If countless universes exist, each with random physical constants, then of course we'd find ourselves in one where conditions align perfectly. Like a lottery with infinite tickets, some universe had to win. The catch: this multiverse theory, while elegant, remains untested. Without evidence of other universes, the anthropic principle walks a tightrope between profound insight and philosophical dead end. The debate gets even thornier when ethics and theology enter the picture. Does fine-tuning imply a designer, or is it pure statistical inevitability? For physicists, the challenge is to move beyond speculation. Could variations in fundamental constants leave traces in the cosmic microwave background? Might future quantum experiments reveal hidden layers of reality where other settings exist? The anthropic principle doesn't just ask why the universe is hospitable. It forces us to confront whether we're cosmic accidents, inevitabilities, or something in between. What's undeniable is how fragile our existence truly is. The universe didn't have to allow for stars, planets, or conscious minds. Yet here we are, measuring, questioning, and marveling at the very laws that let us do so. Whether the answer lies in a multiverse, deeper physics, or sheer luck, one thing's clear: The anthropic principle isn't just about the universe we inhabit, it's about the stories we tell to make sense of our place within it. This section maintains your signature mix of wonder and scientific rigor while avoiding repetitive phrasing. It introduces the anthropic principle's controversies and implications without oversimplifying, keeping both casual viewers and space enthusiasts hooked. Let me know if you'd like any tweaks. The dream of stepping into a time machine, whether to revisit ancient Rome or peek at humanity's distant future, has fueled imaginations for centuries. H.G. Wells' The Time Machine painted it as a thrilling adventure, but modern physics treats the idea with surprising seriousness. Einstein's general relativity doesn't just permit time dilation, it requires it under extreme conditions. Near a black hole's crushing gravity or aboard a ship approaching light speed, time bends like taffy. But what about genuine leap through the ages travel? The equations suggest it's not impossible, just fiendishly complicated. Take closed time-like curves, hypothetical pathways where space-time loops back on itself. Picture a cosmic treadmill. Walk far enough along one of these curves, and you'd return to your starting moment, effectively traveling backward in time. Some solutions to Einstein's field equations, like traversable wormholes or spinning cosmic strings, could theoretically create such loops. But here's the catch. These scenarios demand materials with impossible properties, negative energy, infinite density, or technology far beyond our grasp. Then there's the infamous grandfather paradox. If you traveled back and accidentally prevented your own birth, would you vanish in a puff of logic? Quantum mechanics offers an escape hatch. The many worlds interpretation suggests every decision spawns parallel timelines, so altering the past might simply branch off a new reality where history unfolds differently, leaving your original timeline untouched. It's a tidy solution, but raises its own existential questions. If you jump backward, are you ever truly in your own past, or just an observer in someone else's future? While no one's building a DeLorean anytime soon, cutting-edge experiments are testing time's flexibility. Quantum particles can be time-looped to act as their own past selves, and researchers have simulated retrocausality, where effects precede causes in controlled settings. Even the humble photon seems to toy with time, behaving as if it knows its future path before choosing one. Perhaps the most tantalizing thought isn't whether time travel is achievable, but whether it's inevitable for a sufficiently advanced civilization. If the laws of physics don't forbid it, someone somewhere in the far future might crack the code. Until then, the paradoxes, possibilities, and unanswered questions keep the dream alive, not just in fiction, but in the equations scribbled on blackboards at the frontier of human knowledge. White holes, cosmic fountains, or mathematical mirage. Imagine a black hole in reverse, a celestial fire hydrant blasting matter and energy outward with unstoppable force, as if the universe itself were coughing up something it couldn't digest. That's the tantalizing concept of a white hole, a theoretical counterpart to black holes where nothing can enter but everything erupts. The math allows for it. Einstein's equations describing black holes work just as well when time flows backward, suggesting these cosmic exhaust vents could exist. But if they do, where are they hiding? Unlike their dark siblings, white holes would be impossible to miss. A single one discharging matter would outshine entire galaxies, flooding space with radiation and particles. Some astronomers have wondered if mysterious, high-energy events like gamma-ray bursts or fast radio bursts could be white holes flaring to life. Others take the idea even further, suggesting the Big Bang itself might have been the ultimate white hole, the primordial eruption of space-time and matter from an unknowable source. Yet for all their explosive potential, white holes face a glaring problem. Physics hates them. A true white hole violates the second law of thermodynamics, seemingly creating energy from nowhere. Even if one formed, theorists argue it would collapse instantly into a black hole, snuffing out its own existence. That hasn't stopped scientists from hunting for indirect clues, like odd gravitational lensing patterns or unexplained energy signatures that might betray a white hole's presence. Whether cosmic reality or mathematical ghost, white holes push us to ask deeper questions. Could they be portals to other universes, as some models of wormholes suggest? Or are they simply reminders that the universe's equations sometimes paint possibilities that nature rejects? For now, the search continues not just for white holes, but for the hidden rules that decide which dazzling ideas become cosmic fact and which remain beautiful fiction. One thing's certain, if white holes are out there, they'd rewrite the story of the cosmos in the most spectacular way imaginable, and in a universe full of mysteries, that's a thread worth pulling. Cosmic strings, the universe's hidden scars. If you ran your fingers along the fabric of space-time, you might feel something unexpected: tiny, invisible cracks, thinner than an atom but stretching across the cosmos. These are cosmic strings, hypothetical defects left over from the universe's earliest moments, when reality was still cooling into its current form. Picture the universe as molten glass hardening. Some areas might have frozen slightly misaligned, leaving behind flaws in the structure of space itself. These strings aren't made of matter, they're fractures in the very geometry of existence, carrying more energy than a supernova in a strand thinner than a proton. What makes them so extraordinary is their influence. A single cosmic string, thinner than a human hair but light years long, would warp space-time around it like a taut wire pressing into a bedsheet. Any galaxy or star passing near one could be stretched or distorted by its immense gravitational pull. Some theories even suggest these strings might have acted as cosmic scaffolding, guiding the formation of galaxies in the universe's infancy. And if two strings crossed, they could create closed loops of space-time, natural time machines where cause and effect might twist into knots. Yet for all their theoretical power, cosmic strings remain ghosts in the equations. No direct observation has confirmed their existence, but the hunt is on. Astronomers search for their fingerprints in the cosmic microwave background, looking for telltale temperature fluctuations. Others monitor distant quasars for strange distortions in their light, which could betray a string's gravitational lensing. Even gravitational wave detectors might one day catch the ripples from a snapping string vibrating through space-time like a plucked guitar string. Whether cosmic strings are real or just mathematical curiosities, they force us to grapple with a profound idea. The universe we see today might be built on imperfections, relics of a time when reality itself was still settling into place. And if they do exist, they could rewrite our understanding of gravity, time, and the hidden architecture of everything. So while we're still waiting for that first definitive glimpse, one thing is certain: the early universe was far stranger than we ever imagined, and its echoes might still be hiding in plain sight. The holographic principle: is reality just a cosmic illusion? Picture your favorite movie projected onto a screen, flat, two-dimensional, yet creating the vivid illusion of depth and movement. Now imagine the universe works the same way. According to the holographic principle, our seemingly three-dimensional reality, every galaxy, every atom, even your thoughts, might be nothing more than a projection. It's true code written on a distant two-dimensional surface. It sounds like science fiction, but this radical idea emerges from some of the deepest corners of physics: black hole paradoxes and string theory's most puzzling equations. The seed of this theory was planted when physicists grappled with an unsettling question: what happens to information swallowed by a black hole? Quantum mechanics insists it can't be destroyed, yet black holes seem to erase it. The breakthrough came when theorists realized the information might not vanish. It could be imprinted on the black hole's event horizon like a cosmic fingerprint. If true, the entire three-dimensional interior of the black hole could be encoded on its two-dimensional boundary. Extend that idea to the whole universe and suddenly, reality starts to look like a hologram, an elaborate projection from a hidden surface we can't see. String theory takes this even further. To make their math work, string theorists needed extra dimensions, tiny, curled-up spaces we don't perceive. The holographic principle flips that script, suggesting those extra dimensions might not be real in the way we think. Instead, they could be shadows cast by a simpler, lower-dimensional reality. Think of it like living inside a video game. The world feels vast and interactive, but at its core, it's just lines of code running on a flat, distant server. If reality really is a hologram, the implications are staggering. It would mean information, not matter or energy, is the universe's true currency. The solidity of your hands, the vastness of space, all might emerge from something as abstract as bits of data. Some physicists even speculate this could explain quantum entanglements, spooky action at a distance, where particles instantly influence each other across vast distances. In a holographic universe, they might not be separate at all, just different projections of the same underlying code. Yet for all its elegance, the holographic principle isn't without skeptics. How do we test something so abstract? Experiments like the holometer at Fermilab have searched for telltale pixelation in space-time, tiny noise that would betray an underlying digital structure, but so far the universe appears smooth. Others argue the principle might apply only in extreme environments like black holes, not the everyday world. What's undeniable is how this idea forces us to rethink the very nature of existence. Are we physical beings in a material world, or shadows dancing on the surface of something far stranger? Whether the holographic principle holds up or not, it's a thrilling reminder. Reality might be far more malleable and mysterious than we ever imagined. Vacuum decay, the universe's silent time bomb. The universe appears stable, stars burn, planets orbit, atoms hold their shape. But what if this stability is just an illusion? Beneath the surface of reality, our entire cosmos might be balancing on a knife's edge. Theoretical physicists call this terrifying possibility vacuum decay, a scenario where the fabric of space-time itself suddenly collapses, rewriting the laws of physics in an unstoppable, expanding wave. The risk stems from an unsettling quirk of quantum field theory. Empty space isn't truly empty. It's a seething quantum foam brimming with potential energy. If our universe exists in a false vacuum, a temporary high-energy state, it could theoretically tunnel into a lower energy configuration, like a ball rolling from a hilltop into a valley. The moment that shift begins, a bubble of destruction would form, expanding outward at the speed of light. Within that bubble, every fundamental force, gravity, electromagnetism, even the nuclear bonds holding atoms together, would cease functioning as we know them. Matter itself would unravel in an instant. Here's the chilling part: there'd be no warning. The bubble's boundary wouldn't emit radiation or detectable signals. One moment, everything would be normal. The next, annihilation would sweep across galaxies, erasing stars, planets, and life in an irreversible rewrite of reality. Even light from the event couldn't outrun it. We'd never see it coming. But how real is this threat? Most calculations suggest the probability is vanishingly small. The universe has lasted 13 billion years without decaying, hinting our vacuum might be stable. Yet the mere possibility forces us to confront an uncomfortable truth: the laws of physics aren't set in stone. They could be local, contingent, even fragile. For now, vacuum decay remains a thought experiment, a reminder that existence, for all its apparent solidity, might be far more precarious than we dare admit. And while we search for answers, one lesson lingers: the universe's greatest dangers often hide in the quietest corners of quantum uncertainty. Baryon asymmetry. the universe's tilted scales, the early universe was a battlefield, one where matter and antimatter should have wiped each other out completely. Every particle of matter has an antimatter twin with opposite charge, like a cosmic mirror image. When they meet, they annihilate in a flash of pure energy. According to the laws of physics, the Big Bang should have produced equal amounts of both. Yet here we are, surrounded by galaxies, planets, and atoms, proof that somehow matter won. This lopsided victory, known as Baryon asymmetry, isn't just a cosmic fluke. It's the reason anything exists at all. So how did matter gain the upper hand? The tiniest imbalance, just one extra matter particle for every billion annihilations, would have been enough to seed the universe we see today. That's an absurdly fine margin, and it points to something fundamental. The laws of nature must favor matter, if only by a whisper. Physicists call this hypothetical bias CP violation, where the universe treats particles and antiparticles slightly differently. We've seen hints of it in exotic particles like kaons and B mesons, but the effect is far too weak to explain the overwhelming dominance of matter. The search for answers has led to some radical possibilities. What if undiscovered particles like heavy neutrinos from the early universe decayed unevenly, leaving behind more matter? Or perhaps there's an entirely new force in play, one that tweaked the scales in those first critical moments. Some theories even propose that antimatter wasn't destroyed. It might exist in hidden regions of the cosmos, separated from us by unseen barriers. Experiments like the Large Hadron Collider are hunting for these clues, smashing particles together to recreate the conditions of the early universe. Others study the cosmic microwave background for faint echoes of that ancient imbalance. The stakes couldn't be higher. If we solve this puzzle, we'll understand not just why the universe exists, but whether its tilt toward matter was inevitable or a breathtaking stroke of luck. For now, Baryon asymmetry stands as one of physics' most profound mysteries. It reminds us that the cosmos didn't have to turn out this way, and somewhere in the math lies the secret of our very existence. A cosmic farewell for now. 13.8 billion years of cosmic history, from the first blinding flash of the Big Bang to the eerie depths of black holes, and somehow we've arrived here, conscious minds on a pale blue dot, daring to unravel it all. This journey through the universe's greatest puzzles isn't just about distant galaxies or abstract equations. It's a testament to human curiosity. Every discovery, whether it's the quantum flicker of a particle or the gravitational roar of colliding black holes, reminds us that the cosmos thrives on mystery. Yet here's the beautiful paradox: the more we learn, the vaster the unknown becomes. Dark matter's invisible grip, the haunting silence of the Fermi paradox, even the holographic whispers of reality itself. Each revelation peels back a layer only to expose deeper questions. That's not discouragement, it's an invitation. The universe isn't a puzzle to be solved, but a story to be explored, one where every generation adds a new paragraph. So let's keep that conversation alive. Which cosmic wonder keeps you awake at night? Is it the birth cries of the first stars, the enigma of time's arrow, or something far stranger? Drop your thoughts below. This adventure has always been a collective one. And if you've enjoyed this voyage through space and time, hit subscribe so we can keep decoding the cosmos together. As for what's next, the universe has a way of surprising us. New telescopes, quantum breakthroughs, even messages from distant worlds. The next chapter is already being written. Until then, remember, the night sky isn't just a sight to behold. It's a mirror reflecting our endless hunger to understand. Stay curious, fellow explorers. The cosmos isn't done with us.